Good morning and welcome to the inaugural Additive Manufacturing Workshop for Automotive at the North American International Auto Show. Please welcome to the stage today's moderator, Additive Manufacturing Media Editor-in-Chief, Pete Zielinski.
Thank you. Welcome to the Additive Manufacturing Workshop at the North American International Auto Show. I'm Pete Zielinski. I'm Editor-in-Chief of Additive Manufacturing Magazine. If you've got a copy in your bag, we are your hosts for this event. Thank you for coming. This is the first time there's been an event devoted to additive manufacturing at the North American Auto Show, and we are so pleased to get to bring this to you. Thank you to the Detroit Auto Dealers Association for this opportunity. It is time for this event. Additive manufacturing technology is advancing quickly, still changing. It is becoming clear that additive will have a significant role to play in automotive manufacturing. In fact, we were all set for additive to transform auto manufacturing in one way, and now we should be prepared for it to transform it another way as well. The first way additive was already having an impact: tooling. Additive is a transformational option for making injection molds, assembly tools, jigs, fixtures, certain dies, tooling. But in addition to that, now becoming available, coming to market, are additive systems that are capable of production, capable of cost-effective, repetitive manufacturing at scales, rates, and quantities appropriate for production. Our speakers in the next couple hours are going to speak to both tooling and production, and I'm going to get out of the way. So here's how this program will work. To maximize presentation time, there will be no fixed breaks. Just come and go as you need to. We sort of a late discovery. We discovered we have this stage a half hour longer than we thought we would. So we're going to tack a half hour onto the end for Q&A. After the last speaker, all the speakers will return to the stage for a panel Q&A, so be thinking of questions that you would like to put to all of these experts when they're back on the stage. The auto show main floor will open after we're done at noon, and in closing, I want to be sure to thank our speakers and our sponsors: Carbon, Desktop Metal, Renishaw, Siemens, and Sodic. And now I'd like to welcome to the stage our first set of speakers, Dr. Ellen Lee of Ford and Paul DeLora of Carbon.
Morning, everyone.
Good morning.
Hope everyone's doing well. Thanks, Pete, for the introduction. Hope everyone survived the slippery sidewalks on your walk here today. It's great to be at the North American International Auto Show, where Henry Ford's vision of opening the highways to all mankind, or all humankind, as I like to say, is here. And so it's exciting to be here because this is our guiding principle within Ford Motor Company DNA to provide affordable vehicles, transportation, and mobility solutions for everyone. And so this event at the North American Auto Show for additive manufacturing for automotive applications signifies to me that now is the time where we're going to see continued acceleration of adoption of additive manufacturing to add value for our products for the masses, for affordable vehicles. So with that, my name is Ellen Lee. I'm the technical leader of additive manufacturing at Ford Motor Company for research. And I'm excited to be co-presenting with Paul DeLora, who's a vice president of enterprise partnerships at Carbon, on the work that our cross-functional teams at both companies worked hard to deliver: end-use parts on demand for production vehicles at Ford using Carbon's additive manufacturing technologies. So here's our agenda for today. We're going to go through and present together with first the challenge. We'll start out with why Ford is interested in additive manufacturing, why do we care, and a little bit about the journey that we've seen with additive manufacturing yesterday, today, and tomorrow. And then I'll hand it off to Paul, who will talk a little bit about Carbon, the company and its technology and advantages. Then he'll introduce the 3 production applications in our results, where we're getting value from using additive manufacturing for our vehicles. And then I'll come back and talk about some of the validation details of how we validated the material, the function, the design, and the production process, and importantly, the business case. And then finally, we'll both talk about what's next for each of our companies. So first, why do we care about additive manufacturing at Ford? Essentially, the attributes of additive manufacturing, namely that we can make a 3-dimensional part without the need of a mold or a tool, in addition to the design freedoms of those parts that we can make, provide us with values in efficiency, agility, and performance. So in terms of efficiency, as Pete mentioned, we've been using additive manufacturing for quite some time to make our design processes a lot more efficient, to go through quick iterations in our prototype parts because we don't have to wait for that long step of tooling. And as the technologies and materials continue to improve, we're able to go further and further along that functional testing step and prototyping, making our processes even more efficient. And today we're also using additive manufacturing for those tools and fixtures on our manufacturing floor in our facilities to make those processes more efficient, not only to make the fixtures faster and more ergonomic, but those fixtures work better, providing us with efficient processes on the manufacturing assembly and a more quality product. For agility, additive manufacturing technologies and their benefits allow us to more nimbly respond quickly to the dynamic changes in the market and our complex supply chain. So for example, we'll see how we can quickly respond to niche markets or low volume opportunities that we couldn't do cost effectively with a hard tooled solution. And finally, performance. Those design freedoms that we get through additive manufacturing technologies allow us to focus on how to get the right function of that part by carefully designing the parts with architected structures to reduce weight, improve energy absorption, improve heat rejection for increased surface areas and so forth, by making those structures that are much more complicated than conventional means might allow. And with all of these improvements to our processes and products, we need to keep in mind that we need to meet or exceed all of the requirements for function, durability, and quality that our conventional products meet today. And so how are we doing that? One of the ways is that we've just announced at the end of last year standing up the Advanced Manufacturing Center. This is a unique facility that houses many advanced manufacturing innovations all together in one location, including a lot of additive manufacturing technologies, engineers, operators, material specialists, all working together cross-functionally to bring these lofty goals to fruition. And one of those technologies is Carbon's technology. So I'm going to hand it off to Paul now to talk about that technology.
Great, thank you, Ellen. It's really an honor for Carbon to be here and to be presenting with Ellen and with Ford. And Carbon's vision is to transform how polymeric products are designed, engineered, manufactured, and delivered towards a digital and sustainable future. And we're a relatively young company. We're only about 6 years old, founded in North Carolina, now based in Silicon Valley in Northern California. And our process is quite different from traditional additive manufacturing or 3D printing processes for a variety of reasons. And one of those key reasons is because our process is not a layer-by-layer process. We're able to grow parts such that they are layerless and they have the same strength in all directions. So the quality of the parts is much more like an injection molded part than a traditionally manufactured part, or than a traditionally additive manufactured part. In addition, our print speeds are quite a bit faster than traditional 3D printing or additive manufacturing, in some cases 25 to 100 times faster. That allows us to produce parts more quickly, more efficiently, but it also allows us to access a type of chemistries, reactive materials like epoxies and polyurethanes that allow us to develop and create materials for the first time that are automotive grade, that can meet the durability standards, the chemical resistance standards, the temperature standards for automotive applications, for real end-use applications. Now, additive manufacturing is not new, as we've heard. Of course, it's been around for decades and delivered great value through the use of prototyping, product development, and tooling. And all of Carbon's customers use our technology for those kinds of purposes as well. But Carbon is also very focused on production, on the production of end-use parts. And one of the most prominent examples of that is what we're doing with Additive, to use our technology to make midsoles like this for several lines of shoes. These midsoles are called 4D midsoles. And it's a really unique combination of a material as well as a unique design, a lattice structure that can't be produced via injection molding or compression molding. And it's able to deliver superior performance, superior mechanical response when compared to a foam midsole. And this is by far the highest volume production application of anything that's been done with 3D printing or additive manufacturing for an end-use part. Last year, over 100,000 pair of these midsoles were made. This year, it will be over 1 million and growing beyond that as Additive continues to roll this out across more and more lines of shoes. And that allows us to offer different kinds of economics and efficiencies to our customers, because as the volumes for these kinds of programs and other programs increase, as more and more customers move into production, we're able to lower the costs associated with our technology. And we've done that with our materials. When Carbon first launched, our materials cost between $300 and $400 per liter. A little over a year ago, we reduced that to $150 per liter, and then just last November, we announced a reduction to $50 per liter, which makes it much more economical and relevant for a wider range of applications. And then finally, Carbon is very focused on automotive. We have a number of people in our company that come from the automotive industry, and including at the most senior level on our board of directors, we have real automotive experience. Alan Mulally is on our board of directors, of course, the former CEO of Ford Motor Company, and also Ellen Kullman, the former chair and CEO of DuPont. And she's our lead director as well. And they provide great leadership to us and a real commitment and focus to the automotive market. So as Ellen mentioned, we've been working quite closely, especially over the last year and a half, in order to help support Ford's goals of using additive manufacturing for production in order to improve efficiency, agility, and then offer parts that have superior performance. And we're going to talk about 3 applications here today that are production applications of end-use parts. The first we're going to focus on is an example of improved efficiency for service parts, for spare parts. And additive manufacturing has long held the potential of being of great value for MRO, for service parts, for spare parts, especially for late model vehicles, for older vehicles. And this application is an HVAC lever arm. So it's a lever arm, thanks Ellen, that's used to open and close vents in an HVAC system for an older Ford Focus. And this part was originally produced with 30% glass-filled PBT material and injection molded. But Ford needed to have some new parts made. And it would have been quite time-consuming and expensive to get the tool out and produce these new parts and then have those parts sit in a physical warehouse and have those parts kind of in inventory as well as on the books. So as Ellen will describe, Ford qualified our materials, our epoxy material, as well as our process, and ultimately began producing these parts on demand from a digital file. So replacing a physical warehouse and physical inventory with a digital file that is produced on demand in order to support the service part needs of dealers and customers. And as a result, reduced the lead time quite considerably. So over 50% reduction in lead time when compared to what it would take to bring out the tool and produce new parts. And also completely eliminated the concept of a minimum order quantity. Now parts can just be produced from that digital file when required. The next application, thank you, is an application that really highlights agility and the ability to respond to market needs and market demands economically, especially for low volume vehicles. And this application is an application that is part of the F-150 Raptor for the Chinese market. And in the Chinese market, there's a regulation that prohibits the use of certain kinds of lights, including spotlights, that are part of vehicles here in the United States. So Ford needed to remove the spotlight and remove the switch in the instrument panel that controlled the spotlight and cover that switch, or the opening for the switch, with a delete plug. And it's a relatively low volume scenario for the Chinese market. And so it would have been quite expensive and time consuming to stand up a tool, to design that tool, stand it up, and then produce the parts. One of the great values associated with our process is the ability to quickly design parts, print them, and then test those parts and be able to cycle through many different designs in a short period of time. And that's what Ford was able to do here, going through over 14 designs in 19 days in order to design and test the parts that are now part of that F-150 Raptor for the Chinese market. So they were able to get the right design, and during that process also experiment with different looks, different textures, different lettering, because all of that is essentially a free part of the process. It's just a digital file, so we can quickly and easily add textures, we can add logos. So the Raptor logo is prominently displayed on this delete plug, so it's a visually pleasing and aesthetically nice part now. And this is just an example of how Ford is able to economically make parts for low volume production. Thank you. And then the third application we're going to focus on here is an application that highlights the ability to take advantage of design freedom, the design freedom that comes from an additive process, in order to produce a part that performs better, offers some superior advantage relative to what would be possible if you were injection molding. And this is a bracket that holds a cable associated with an electric parking brake system for the Mustang GT500, which was just announced earlier this week. And in prior versions of the vehicle, the bracket would have been stamped out of steel, and there would be two versions, a left-hand version and a right-hand version. Carbon and Ford worked together in order to create this design, a unique design that would be very difficult to injection mold, that is a mono design. So it works on both the left-hand side of the vehicle and the right-hand side of the vehicle, which improves the ease of installation. And during the development process, we were able to test out different designs and get feedback from the ergonomics team in order to determine the optimum design for installation. And not only that, when compared to the weight of stamped steel, it's over 60% lighter compared to what the alternative would have been. So it helps support Ford's vision and goal of lightweighting vehicles, taking mass out of vehicles, and helping them perform better. So all of this was done, again, in a digital process, being able to go through iterations quite quickly, and ultimately get a design that's optimized for the requirements for this market and have a superior performance. So I'm going to hand things back to Ellen, who's going to talk a little bit more about the qualification process that Ford has gone through to qualify Carbon's materials, our printing process, the functions of the parts, as well as the business case.
Thank you.
Thanks.
So as Paul said, I'm going to be talking about all the validation steps and the details. So the first was the material validation. All three applications that Paul introduced that we're using today in production use Carbon's epoxy-based material EPX82. And because the applications have different functional areas that they're covering, ranging from the interior to the climate to underbody applications, we had to test to all of the functional applications for all of those specific applications. So for example, in our interior application with the Raptor delete plug, not only do we have to pass fogging, odor, and flammability, as do typical interior components, but the most challenging part was to pass all of our interior weathering specifications. So for the particular application of that plug, after exposure to the amount of UV that part is subject to, we not only had to retain properties, but also the appearance of that part, as Paul talked about, because there was no secondary coating protecting that. For both the interior and the underbody application for the EPB brake bracket, we did have to look at fluid and chemical resistance for all sorts of chemicals ranging from suntan lotion for interior applications to motor oils for the underbody applications, which all passed. And then finally, for both the climate control application in the HVAC lever arm, as well as the EPB bracket in the underbody, we needed to consider elevated thermal performance and heat aging for different scenarios and exposures. So these families of applications that we tested towards are qualified for future applications as well for EPX82. Great. So the next step was looking at the functional validation of each of the parts. So these consisted of component level testing, vehicle level testing, as well as assembly level testing when we had to assemble the parts into the vehicles themselves. This picture that you see here is an example of a benchtop fixture to test some of the vibrational exposures for the EPB bracket that went under body. In addition, things like on-vehicle testing on the track allowed us to test for any potential stone impact functions that the bracket would need to survive. And finally, a lot of the ergonomic level testing that Paul kind of alluded to with the team of engineers, as well as torque testing for some of the loading for that functional part were tested. Similarly, for the lever arm, that function was tested as well. They're subject to all of the same design verification test requirements as our conventional components and did pass all of these. Next was really to understand the validation of the process and the production of the manufacturing of a production level part. So the parts were designed in such a way so that we could ensure repeatable and reproducible results from part to part on the print platform, from print to print, and from machine to machine, to minimize any variations that we would see in any of the parts there. So along the way, to help us, we created DFMEAs for each part per their engineering requirements, as well as PFEMAs to understand the entire process, following a standard PPAP or production part approval process. So this paved the way for us for future additive manufacturing applications for parts to understand what differences there are from conventional manufacturing. To that point, we did find some distinct advantages using the digital workflow of additive manufacturing that give us advantages over conventional manufacturing. So as you see in the picture here, we're able to apply individualized tracking and serialization to every single part that is printed, including unique identifiers, including what printer, the project, the position on the print platform, as well as the batch on that printer for the part. And in this way, we're able to better track the security as well as part provenance for all of the parts that are printed. So finally, and importantly, the business case had to be validated, that we were indeed receiving the values that we were looking for, moving to the carbon additive manufacturing process from a traditional process. It may seem quite simple here on the screen, but we're not just trading the CapEx for printers to machines and tooling. It's true that now our digital file becomes our digital tool, and we have significant cost savings from hard tooling. But in materials and labor, materials might be a little bit more expensive, but we do have more efficient and optimum use of the materials where we place the materials for the function of the part. And as we move towards manufacturing innovations, including machine learning and automation, we're moving towards a lights-out operation to reduce the labor costs even further. But in addition to this, there are many more additional value propositions in soft savings, including the shortened timeframes that we've talked about, being able to iterate quickly through designs, having improved performance through weight savings, as well as the convenience and the agility of print on demands. So this is all to say that the validation must consider the entire value chain for a good business case. So to summarize that all together, we found that the advantages that Carbon's additive manufacturing technology provided, including the speed, the robust and durable materials, as well as the design freedoms that we were afforded, allowed us to get to the goals for automotive value in efficiency, agility, and performance. So what's next? At Ford, we're continuing to look for new sources of value, continuing to migrate service parts and low-volume productions where it makes sense when the technologies and the materials are ready as we develop new, improved, faster, and robust materials. In addition, looking at those series production applications, moving towards higher and higher volume, as well as mass customization, and then being able to realize distributed sourcing and distributed manufacturing to print what we want, where we want it, when we want it. And I'll hand it over to Paul now to talk about what's next for Carbon.
Thanks, Ellen. Carbon recognizes that we're really at the early stages of this journey of moving to production applications in the automotive industry. The automotive industry appropriately has a very high bar of what's required. We're thrilled to be able to now have Ford's first production applications using an additive manufacturing process for polymers in production. But we know that we Carbon need to continue to develop our own capabilities, enhance what we offer. And that includes new printing capabilities, including larger build platforms and new features associated with our hardware. That includes, importantly, more and more materials for automotive applications. So we have the epoxy 82 material, which was used in these applications referenced today, and we have a roadmap of materials coming out this year and next year that offer different kinds of characteristics, higher temperature performance or different types of impact strength as examples. And we're going to continue to develop more and more materials for the automotive market because that opens up different kinds of applications and allows you to take advantage of these capabilities for different kinds of parts. We also believe that there's a lot of opportunity on the design side to take advantage of things like topology optimization and lattice designs and being able to produce structures that weren't possible to be made via an injection molding process. So we invest in developing new tools to support that as well, especially on the lattice design side. And then also supporting the desires of our customers to have lights out manufacturing and being able to automate the end-to-end manufacturing process using our technology and developing capabilities to support that and support and interface with the robotics that are used today in factories. Now, of course, to accomplish this and what we want to do in the future, it requires a close working together collaboration between Carbon and Ford, and we've been blessed to be working with Ford now for almost 5 years and quite closely over the last year and a half on these applications. Ford has provided great visibility to us and insight to us in terms of the requirements and what's required for the materials and our process in order to be viable for the automotive market, and that needs to continue. And then we've spent a lot of time with Ford training on our process and learning the nuances of their processes and identifying these applications, identifying and then designing and helping to develop these applications. And as we've done that, these cross-functional teams have worked together across wide aspects of Carbon as well as wide aspects of the Ford organization, including not only the research teams and the materials engineering teams, but now also product development, including the Ford Performance team, the FCSD team, or the Customer Service Division, and also, as Ellen mentioned, now manufacturing with the new Advanced Manufacturing Center in Redford, where these parts are produced. And because we're now involved in production, doing things like quality and procurement and supplier technical assistance and working closely with our organizations there is really critical. So by doing that, we've been able to help support Ford's goals of using additive manufacturing for production, for improved efficiency, improved agility, and then parts that perform in a superior fashion, superior performance. And we look forward to doing more of that together with Ford and with others in the industry over time. So thank you very much for your attention here. We look forward to answering your questions in the panel and talking with you later today. Thank you.
Thanks.
Please welcome to the stage Kevin Brigden, Additive Manufacturing Advanced Concepts Lead at Renishaw.
Good morning. Thank you for having me. Thank you for coming along. This is my first time presenting in front of cameras, so if I'm not entirely sure where to look, please forgive me. I'm not staring at anyone in particular. As you've no doubt guessed already by the accent, the funny voice, that I'm from over the other side of the water. I'm actually based in the Chicago office in Renishaw's efforts over there to bring about the mass use of additive manufacturing in the United States. What I'd like to talk to you about today is our vision for how we can declutter and improve the landscape of additive manufacturing, particularly in automotive. But this presentation is perhaps slightly more generic than just focusing entirely on automotive. We want to talk about the landscape in total. I'd like to, through the medium of clip art, take you on a quick journey over the last 10 years of additive manufacturing. Early in the decade, you have this bright hype, this blinding hype surrounding the technology, and it's just pure excitement. Everyone's talking about this idea that you can print anything that you want to, that it will replace CNC machining, that jobs are going to be lost by the hundreds, thousands. And by today, we know that that's entirely nonsense, right? We know that from the trajectory that additive has gone on, that in actual fact, we're a long way from that. But pretty early on in the decade, we begin to identify the first few factors that were going to prevent widespread incorporation of the technology quickly. So, whether we're talking about certification in aerospace or, we're talking about productivity, particularly in automotive, these are the first things that we start thinking about. And then immediately, once you start drilling into those particular areas, we start having secondary areas where we're needing to drill down further and look into further detail. And eventually, you get to the point where there is no more hype because it can't actually shine through. Okay, and there seems to be this overwhelming need to fully understand the technology before we can incorporate it in our manufacturing environments, particularly in areas where we want to do volume production, such as automotive. Renishaw has encountered this before in the metrology industry, in the metrology market. So obviously, Renishaw is most widely known for our manufacturing of probes, CMM equipment, machine tool equipment, and also automated gauging. So our business is process automation and control. That's where people generally know Renishaw. Whenever we have a show where we're showing additive equipment, the number one thing that people say to us is, oh, I didn't realize that you did 3D printing as well. I always thought you guys were just the probe guys. And so in order to change that, we're constantly having to put out this message that automation of process and control is what additive is all about as well. So in order to bring the technology into widespread use, Renishaw is ideally placed with our history. And so one of the ways in which we went about trying to achieve that with industrial metrology in particular was we had this ethos around the process pyramid, the process control pyramid, wherein the products that we designed and developed could be categorized according to the role that they were filling in the manufacturing environment. So, for example, in the process foundation, there we're talking about the calibration and performance products, such as our bull bar products or our laser calibration products. So we're actually trying to make sure that the machines that we're working with, CNC mills, lathes, whatever, are actually capable of achieving the tolerances that we're aiming for in the first place. Secondarily, we're also then got machine tools, so we're talking about process setting and in-process control. So we're talking about this idea of making sure that the workpiece is actually set up as we require. The tool is actually behaving how we require. We're monitoring tool wear and adjusting accordingly. In-process gauging as well, so you're taking the part off of the machine onto a gauge and very quickly in an automated fashion getting an understanding of how in control the process is. So we can very quickly identify whether or not we need to make adjustments to the process on the fly. So for example, the incorporation of offsets or modification of offsets in response to tool wear and things like that. And then finally, the stuff that Renishaw was always well known for the most was the CMM inspection equipment and styli equipment, but also the fixtures on which all of this metrology work is done. It's no good having all of this fancy equipment if you can't trust the means in which you're setting it up in the first place. So Renishaw moved into developing those products as well. So without wanting to veer off too much into metrology and the deep darkness that can go on with there, what I actually want to do is tell you about how with additive we're taking this similar structured organizational approach and trying to apply it to a technology that can, on first appearances, be so vast and complex as to appear impossible to get under control. So the process foundation equivalent for Renishaw is our solution centers. And in our solution centers, what we're all about is a two-pronged approach where we're developing competence in our customers, and that's not intended in a pejorative sense. That's in saying that competence is knowledge through education, skills through training, and experience through practice. Secondarily, we're then working on developing the solution that our customers are using. So actually working in the technological sense of developing a product for a specific material processing strategy and a specific platform. Okay? So in terms of product design, what we're talking about is a handful of collection of specific application types. So whether we're working with HIETA in heat exchange products, or we're working with competitors in the America's Cup on hydraulic control devices, or we're working with Ferrari Formula One on engine components, or whether we're working with automotive partners in the development of productionized solutions for production volume of AM components. In terms of the process development, we're working on helping our customers understand how to develop the alloys of the future. So for all of the additive players are providing standard parameter sets for processing all of the various powders that are available. But Renishaw goes a step further than that and provides customers with the tools to actually develop their own material properties for specific applications. So these are alloys that may not yet even exist. And none of this is worth anything without selecting the correct platform for the processing to take place on. So whether that's one of the single laser flexible material machines that everybody is by now very familiar with in the industry, or one of our multi-laser systems where we're increasing productivity massively to try and meet the demands of the automotive industry. You know, and in between we have, for example, accessory kits where we can reduce the volume of powder required for development work. So rather than having to commit to hundreds of pounds of powder, you know, a company can actually start doing development work with maybe a dozen kilos of powder or a dozen pounds of powder, much smaller volumes, much less investment up front, and all done on a Renishaw premises with Renishaw staff, enabling much faster cycle development times. So our solution centers, we have them all over the world. We're focusing on key markets. There has actually been another one opened up in Spain since this image was generated. In the United States, we have two sites in particular that we work from. Our North American headquarters, which is just outside of Chicago, and we have also a center here in Auburn Hills, which at the moment is focused on industrial metrology. But it provides us the ability, as the automotive market matures and develops, to start bringing additive technology closer to the customer as well. So our equivalent in additive of process setting would be the build software that we use to actually generate the build designs in the first place. So Renishaw's solution to this is our quantum software. Now, practically speaking, build software is build software is build software. They all pretty much do the same thing. And quantum's no exception to that. It's not doing anything necessarily over and above what a lot of the competitor software is doing. In fact, in many cases, the competitor software has features that quantum doesn't have. But the reason why we developed quantum in the first place is because it was a stripped back, ready-to-use piece of software for our machines where we trimmed off all the fat. We were only putting in features that were relevant to our users of our equipment. But it also meant that tools that exist in other software packages could be developed specifically, and their performance could be improved and increased when a user is using a Renishaw platform machine. So, for example, our material development tools within the software, which we train our customers to use so that they can develop their own alloys, we have the ability within the software to very rapidly iterate and very rapidly adjust laser parameters, so things like power, point distance, exposure time, all of these variables. In fact, in the Renishaw equipment, there's 174 different variables that can feasibly be adjusted, so that the user can actually produce a distributable parameter set that can be locked down and distributed within the manufacturing environment of the company. Similarly, for the multi-laser systems, because we've developed our own software, that means that we have our own means of trying to control how a user, or enable a user, should I say, to assign lasers in the build volume. So two examples here might be where you have a number of parts on a plate and then a single large part. In our software, that enables you to go on a number of different strategies. So for example, you could go along the route of assigning one laser per part, which is typically the most efficient way to do it, particularly when you're operating in multiples of 4, when you have 4 lasers. But things to bear in mind when you're using multiple lasers and multiple parts is how those lasers interact with one another. So again, that's where material development training kind of loops back around and that iteration work gets involved. Also, when you're using multiple lasers on a single part, then you're interested in how the lasers interact at the boundaries of where the area where they're scanning on any given slice. So these are all factors that need to be taken into account, as is the actual utilization of the laser. So in those examples there, you can see that because in the top row with the 4 hydraulic manifolds, we're assigning one laser per part and scanning left to right, we get the best utilization. And the way that you see that is that there's no overlap between any of the 4 traces. When you look at the bottom traces, you can see that there's overlap where there's lasers idling, essentially, during any given layer. And it's through software tools in Quantum that we can help to try and minimize those idle periods. In-process control is one of the buzzwords that's going on with additive at the moment. And the fact of the matter is that there isn't really a great deal of in-process adaptation and closed-loop control going on in the additive industry. And what there is it's iffy at best, okay? Renishaw's approach at the moment is two-pronged. Again, we have 2 products in particular, Infinium Central, which is essentially a data capture and data acquisition device and a data interrogation device. So for example, seeing the status of machines in a workshop, the productivity of those machines, the sensor output, so for example, temperatures, pressures, voltages, things like that, allowing remote troubleshooting, particularly useful in large manufacturing environments where service engineers for a company, or for our service engineers for that matter, might not be on site. We can potentially help to remotely diagnose issues. But also the need to have access and administration controls for various aspects of the manufacturing process, so uploading files, accessing data, and so on. And also everybody's got to have a mobile app because it's 2019. So, the other aspect of the in-process control is the one that's getting everybody excited. It's the one where we're actually capturing data directly from the build itself. So, because Renishaw is a manufacturing company in additive, which is somewhat unique in the sense that our machines are manufactured entirely by us. We're not a black box user wherever we can help it. That means that the degree of vertical integration that we can achieve with our products goes far and away beyond what else is happening, okay? And that's a double-edged sword because it means not only do we have total control over what we're doing, it also means that we're learning all of these lessons on our own, and we're going into areas that have never been touched before. So one area where that's particularly exciting is the idea that we 3D print now components for our own machines. So the 500Q Galvo block for our 4 laser system is actually printed on the machine itself. So we have prototype machine 1 that started printing the others, and so on and so forth. The benefit of which is that the additive design, I'm hesitant to say freedoms, but ideals that you can incorporate, such as conformal cooling and geometric complexity, are incorporated in the design of this component, meaning and allowing us to make a much smaller unit and allowing us to get the lasers much closer together and process through a single window. Now, without going into too much of the nitty-gritty of that, what that means really is that any single laser in our 4-laser system can scan anywhere in our build area at the same time. So in theory, all 4 points could follow each other around on a spot if we wanted them to, okay? Many of the competitor systems, you can't do that because each laser has a separate window, and what you find is that the build area is actually split up into different areas addressed by a single laser. So we have the flexibility there to do very different things. And another thing that it gives us flexibility for is to insert and install laser sensors and melt pool excuse me, sensors inside the machine directly, because we design the galvanometric system. So we're not having to compromise on that. So for example, our Infinium spectral system, we have laser view embedded within the system, but we also have melt view embedded directly in the system. And that gives us the ability to get feedback on energy emissions, but also feedback on positional data as well. So for example, that means we can start building 3D models of data that we can go and view post-process and view two builds side by side and compare the data. So in other words, what we have at the moment is an in-process gauging system, like our equator system functioned in a manufacturing scenario, where we can actually check the performance of the machine in build and make, well, in theory one day, make adjustments as we go. Okay, so some example outputs. So you've got your melt pool there. So what we actually get out in the data format, we can, at the end of a build, program into a 3D rendering, which allows us to actually zoom in, slice layers and things like that. But immediately, almost in near real time, so it's actually at the end of a layer when it's compiled and uploaded, we can view 2D data pretty much immediately. The 3D data at the end of the build, we can then start rendering the full model and comparing it to the slice data, for example, that we generated. And then the post-process monitoring of additive is obviously a large area. And again, I'm not going to spend too much time here, because at Renishaw, that's what we do. All right? So we don't really need to spend a great deal talking about it, because people know that that's what we do already. The inspection and control of machined parts in particular, but also increasingly additive parts, we're already set up to provide the solutions for that as we go. So to summarize, because this is the kind of topic where I was hoping that we're going to get plenty of questions, basically the solution that we see for additive is very, very similar to the solution that we see for metrology, in terms of it's an organized structural approach to the number of problems that additive can raise. Whether it be the process control, whether it be process inspection, whether it be design for additive manufacture, whether it be development of new alloys. Renishaw has got a strategy, a global overall strategy for trying to handle that development and try and ensure that the customer gets back through to seeing that bright hype again and getting excited about the technology rather than nervous about it. So I think with that, I'll wrap up the presentation, and if you guys have got questions, we've still got 10 minutes to go through some questions if you'd like. No? Okay, well, we've got the panel discussion at the end if we want to run through some questions at the end. Thank you very much.
Please welcome our next speaker, Evan Syverson, Additive Manufacturing Business Development Manager from Sodic.
All right, good morning, everybody. So I'm the Additive Business Manager for Sodic Inc. We specialize in metal 3D printers, in particular hybrid systems that include both additive and subtractive components. So don't be surprised if I casually mention some of these hybrid systems throughout the presentation. So our big focus at Sodic is in 3D printed mold tools. So injection molding tools and extrusion dies, that sort of thing, that utilize 3D printing to kind of innovate and improve the performance of these tools. So probably the biggest thing that most of you are going to be familiar with when it comes to 3D printing mold tools is going to be conformal cooling. It's a topic that there's been a lot of buzz around, but I think that in terms of industry adoption, it's still been a little bit reticent compared to where it can be given the substantial gains that we can make. And as part of this presentation, I'll kind of cover what these gains look like, what the process is to produce these additive tools, and then also what some of the challenges are that people have faced that have kind of inhibited progress to this point, as well as some of the solutions to get around some of those challenges. So the reason that conformal cooling has been such a big topic comes down to what the actual cycle of a plastic part looks like. So when you look at the cycle of a plastic part, mold open time, mold close time, filling stage, packing stage, these all have relatively small times within that total molding cycle. Where you actually see the biggest time waste, if you will, is actually in the cooling stage, which at its worst can take up to 60 to 70% of the actual total cycle time of that plastic part. But this actually is an opportunity for improvement moving forward, because if you have this very disproportionate time scale for that cooling stage, it means any improvement that you can make to that cooling stage will also have a disproportionate effect on the total cycle time of that plastic part. So this creates a really great opportunity for reducing cost, improving efficiency of manufacture of those plastic parts. So looking at one example, this is a seatbelt clip that we've actually been producing as SODIC for one of the large automotive manufacturers. In our original design, we used standard two-dimensional gun-drilled water lines. But that design had about a 20-degree delta from the hot spots on the surface of that mold to the coolest points on the surface of that mold. And what that ended up doing is it gave us deformation of the part that was more than a millimeter and a relatively long cycle time for what the part was. But in the course of switching over to a 3D printed mold that used conformal cooling, what we actually were able to do is we virtually eliminated those hot spots. We created a delta that was basically 1 digit rather than being 20 degrees. And we were able to eliminate the projected deformation of that part down to 0, which is quite successful. What that ended up meaning in practical terms is that we actually reduced the scrap rate of those plastic parts while also improving the total cycle time by around 22%, which is pretty substantial. Let's talk about another example. This is a electronic vehicle connector mold, which we've also produced. You can see in this cross-section the conformal cooling lines. They're actually built into the mold itself. One of the questions that comes up, and this is a great example, is comparing conformal cooling, being a new process that requires a little bit of a steeper learning curve and some specialized equipment. How does this stack up to some of the existing solutions that we have? Why not just use a beryllium copper or some other kind of specialty material that has really great thermal properties that you could make an insert out of, as we kind of traditionally have over the past decade or so? Well, the reason is this. Not only is beryllium copper and some of these other specialty materials also expensive, also difficult to work with traditional EDM equipment, partially because of that conductivity, but the performance gains still are limited. What we see here, even with conformal cooling versus beryllium copper, is that conformal cooling produces still a 9% reduction in total cycle time of that mold. But where you see real gains is you actually improve the life of that tool by over 50%. That means that a tool that would have gotten 20,000 shots could now get 30,000 shots by switching from a beryllium copper to a 3D printed steel. So that's kind of some of the impetus for where the added value can be for 3D printing. But in order to really understand where it can be and what some of the challenges are for implementation, you have to dive a little bit deeper. So the process itself is relatively straightforward. Most powder bed 3D printers, which make up about 80% of the market, most of them operate in fundamentally the same way, where you have a stationary powder bed of 20 to 40 micron powder, and that is selectively melted by either an electron beam or a laser that produces a melt pool kind of in the profile of the part that you're creating. You would then add new material on top, use that same laser to melt in profile on top of that previous part, and those two layers would bond together. In our case, if you're doing a hybrid system, you would have the additional step of periodically, after binding several layers together, you would machine the surfaces to get a higher polish, higher surface finish, higher accuracy, before resuming printing, adding new material, melting it, bonding more layers, and ultimately machining again. But in essence, that process is relatively straightforward, and you'll see it kind of across manufacturers. in order to get a better idea of what that process looks like, it sometimes helps to actually see it in action. So you can see they were filling that raw material, that powder, very fine-grained, into the build chamber. This simulation is just showing what the laser process would look like. But here you can see the final layer being sintered as well as machined kind of in process to produce your finished part. So after evacuating your chamber, what you ultimately end up with is a solid piece, which in this example is just essentially a trinket or a test part. But those hollow spaces could easily be conformal cooling channels, detailed surfaces, anything that you'd need it to be. So the process is mostly straightforward. So why has it been such a challenge for the most part to implement some of these really revolutionary technologies and experience the gains that you could achieve? Well, probably the number one limiting factor has been the limited accuracy of 3D printers up to this point. So in general, 3D printing has been considered a near net shape process. So you're not ever able to really achieve a finished part historically. Because of the internal stresses and the lack of accuracy from the lasers, normally what you'll have to do is you'll leave machining stock on that part. Heat treatments for these parts, which normally has to be done, will cause movement in the steel. The lack of laser accuracy leaves a pretty rough surface finish. So we're leaving, in general, about a millimeter and a half of machining stock on top of these parts, just to ensure that those conformal cooling channels are in the part and that those surfaces can be equally accurate. So you can see here on the left, we have kind of the as-printed, only printed part, which is basically just a solid piece of rough steel, versus the finished part, which you can see has considerably more detail. It has deep ribs, it has through holes, lots of features that aren't reflected on that part as printed. And one of the problems with this, in addition to adding extra processes, is that it adds significant cost. So you've added the cost of purchasing and utilizing a 3D printer, but now you still have to do your machining, you still have to do your stress relief, you still have to do all of these other operations that you normally do in order to produce a 3D printed part. And one of the biggest challenges in achieving that has been the internal stresses of that part. You know, it is a hot process done layer-wise, which means there's going to be a thermal gradient across that part, which is going to cause those stresses to express themselves in unusual ways. One of the other roadblocks for using 3D printing for producing mold tools is the impact that it has on venting. So a lot of streamlined designs for mold tools where you can reduce assemblies into a much lower number of components for those tools. Part of that process ends up eliminating a lot of the fitting lines that would traditionally allow for venting of those molds. And the incentive for using those molds, using those lines for those molds, is that you're going to be able to improve part quality, you'll reduce overshot, you're going to reduce burn marks, a lot of these parts, a lot of these elements that would reduce part quality and end up increasing your scrap rate. So by 3D printing, you're also increasing a lot of the use of some of these specialty materials, your porcerax, your specialty areas for special venting. So it creates a lot of additional challenges kind of as a byproduct. So some of these would-be challenges need solutions before we can really move on and see real added value from these 3D printed parts. Obviously, the implementation of conformal cooling channels has a lot of opportunity, but if it's going to significantly increase the cost of your tool, if it's going to increase a lot of your lead time, it's not feasible until some of these challenges are solved. So what do some of these solutions look like? In one case, for probably that largest issue of the internal stress and the accuracy of your parts, there's new technologies on the market coming out for stress relieving these parts in process. Essentially what that means is that you're going to achieve a much more accurate part at the end of that print, which is going to reduce the amount of secondary operations that need to be performed. So depending on the material you're using, it can have differential effects of temperature on that material. So materials that lack carbon will have very traditional linear contraction when it cools and linear expansion when it is heated. So as that part is cooled after that hot process, you'll see the part contract and have almost a potato chip effect. Whereas materials that contain high levels of carbon actually see expansion during that cooling process because of some of the changes that are occurring in the microstructure of that material itself. And this is one of the biggest challenges of trying to predict the thermal deformation of those parts as they cool after they've been printed. And this is one of the reasons for leaving so much machining stock on those parts. But in part, these transformations are actually predictable based on some of the chemical composition of those parts themselves, particularly of carbon, which has a very predictable change in the crystal structure, which will determine just how much it expands during the cooling process. Which means if you can balance that expansion with the anticipated shrinkage due to heat, you can actually achieve a much more stable part and have a much more reliable tolerance across that entire part. What that means ultimately to you is that your lead time is reduced, your part quality goes up, and ultimately 3D printing looks like a much more achievable option. So in 2018, just this last year, there was a patent issued on this technology to Sodic for stress relieving in process some of these high carbon steels. So what does it look like for using this stress relief process versus not using the stress relief process? Well, you can see on the left here, what we have is no stress relief process, and it's very predictable exactly where cracks will start to form due to this stress. So you can see these notches, these points of inflection where cracks traditionally form and where you can expect them to form in general. But on the right, you can see these very same notches, these points of inflection, where there's no cracking occurring in any instance on any of these test samples. So all of these tokens are produced stress relieved before they ever leave that machine, which means that you're not worrying about cracking, you're not worrying about that part changing shape after it's been made, which means the amount of machining stock and secondary operations that you're performing is significantly reduced. Here's an example of a part made in 420 stainless steel, which is a material that's been a real challenge for a lot of 3D printer manufacturers because of just how sensitive it is to temperature. It has a very high rate of change across that part as temperature changes. So this part's about 180 millimeters by 150 millimeters. And across that entire length of that part, after removing it from its base plate, removing it from the machine itself, it maintained a tolerance of about 15 microns, which for a high carbon steel is unheard of. And this type of technology has a lot of application for not only other high carbon steels, but also other materials that have unique properties when exposed to temperature or unique problems of internal stresses. So it creates a lot of opportunity for new and innovative materials that have previously been a real challenge for the 3D printing industry as a whole. So this creates opportunities not only for exotic materials, but also those materials that are going to be very well known to tool makers, D2, H13, those types of things. Looking a year down the pipeline, they might look a lot more reasonable than they have to this point where they don't exist. Going back to the other issue of venting, we can talk about controlling some of the characteristics of that metal based on the build process. So a lot of the time, high density can be very desirable. Obviously, a high density part is more durable. You can get it to a higher polish, so optical molds can be achievable. These things are all very desirable. But when it comes to venting a part, sometimes that porosity can actually improve the performance of that part in certain situations where you're getting burn marks because of those gases that aren't being released. So you can actually see here, this is a piece of steel that we've 3D printed, that you can actually see air passing through the pores of that steel. So actually being able to characterize the properties of these materials based on the settings you're using, based on the laser speed, the laser power, having these known variables where you can control selectively certain areas of your part in order to produce optimal venting conditions. This is another area where your design consolidation and streamlining your mold design doesn't have to mean worse venting. It can actually mean improved venting. And finally, let's talk a little bit about the mold life cycle. And there are a few specific questions that come up repeatedly, one of which is actually caring for a conformally cooled mold. Now, a mold that has very straight water lines can seem a lot more straightforward to clean. And a lot of the time, people will wonder, well, if I have this very serpentine cooling system in my mold, how do I get that cleaned? Well, there's actually a lot of products on the market commercially available that are more than capable of cleaning those water lines. One, not even a sodic product, but just one that we happen to use, would be called water reamer, which basically just uses pressurized water with a little bit of acidic additive to run through those water lines and clear out a lot of the corrosion, a lot of the scale buildup, a lot of that stuff, regardless of the internal geometry of that part. So caring for these conformally cooled molds doesn't actually have to be all that complicated. I think this product is available for something like 20 grand in the US. It's not a very expensive investment, and it cleans both additive manufactured molds as well as traditional molds. So it's not as complicated as I think that it's sometimes perceived to be. Also, let's look at repair. Regardless of having been 3D printed, many additive materials are highly weldable. They'll behave very similarly to the sort of bar stock that they'd be comparable to. So a 420 that's been 3D printed can still weld the same way that a 420 stainless could weld if it was just a regular stock material. So these things don't change the actual care of your mold all that much. Likewise, because you're 3D printing based on a 3D solid model, the repair process can actually be simplified. So rather than having a very complex repair process, you can actually run the same program you used to produce your mold in the first place. That same model can be used for repair by selectively setting what layers you want to start from and printing only those layers that need to be repaired. So this can have real implications for the care and the ease of maintenance for a lot of 3D printed molds that are being used today and hopefully in the future. So just to review, conformal cooling has real impact on the cycle time and the cost of plastic parts that are being produced. But there are certain, let's call them roadblocks on the path to having full implementation of 3D printing processes for your mold tools. But ongoing development in the 3D printing technology can improve your tolerances. It can improve the life of your mold. And I think that taking a step back and seeing the forest for the trees can actually allow you to see that maintenance of these molds is actually not as complicated as it might be perceived to be. There's no reason that cleaning water lines or repairing a mold is any more difficult on a 3D printed mold than it would be on a traditional mold. So I think that some of these roadblocks might be simple perception errors, and some of them are just the state of the technology as it's been previously. But by kind of keeping an eye on the future of the technology, the new patents that are coming out, the new features that are coming out, I think we can see a lot of ways where some of the roadblocks that might have made you think twice a year ago might be non-issues today. Or they might be things that you might want to take a second look at now and see, is this something that I can get real value from based on the technology that's available? One thing that I do want to point out, we do have a local supplier right here in Detroit. Proper Group is a supplier of mold tools and plastic parts. They do utilize 3D printing technology for these types of applications. So for people that are interested in maybe experimenting a little bit with the technology, but that maybe want to get their feet wet before investing close to $1 million in a machine, going through a vendor like this might be a great way of experimenting with some tools that could add value without kind of exposing yourself to some of the risk of investing before you're ready. All right, I think that about does it.
Chris Weber, Director of Additive Manufacturing Portfolio Development at Siemens PLM Software, and his co-presenter, Douglas Ramsey, Chief Development Officer at Hackrod.
Good morning. Really excited to be here this morning. Have a chance to talk to you about what we're doing in additive manufacturing. I got to say that I've been in manufacturing for 33 years now. That kind of stings a little bit in one way. But I can honestly say this is probably the most exciting time in my career, to be at the forefront of something completely new. I wasn't around at the time where they actually figured out how to stamp metal or to, cut a block of steel, and start the whole CNC component. But this is something that is very, very transformational. And we see to be very transformational within Siemens ourselves, because we actually make products, right? Industrial products, as well as software. So I'm going to cover a little bit of both those items today. So I'm going to cover two use cases. One, an external use case with a project with Bugatti. The second use case would be internally, what we're doing in Siemens power generation. And then the third is with our partners, Hackrod, to talk about what we're doing together there. So what's really interesting, in the last year and a half or so, my travels in additive, is really seeing getting from the prototyping stage into the holy grail of how do I productionize the parts? How do I get repeatability, right, in mass production, or if I do lot size of one? How do I do that? That's the difficult part. Pretty exciting, right? Everybody dreams of having one of those. Very few get a chance to drive a Chiron. But there's four things that you really got to think about is in order to do that in a production environment, you need to digitalize the process, you need to design the parts, optimize for industrial additive manufacturing within a PLM system, you need to predict and eliminate printing issues before you start to print the part, and then finally you need to automate the production. So when you see here in this example of the Bugatti is how do you keep a car that travels over 248 miles per hour on the ground? When you think about it in perspective, a jumbo jet takes off the ground at 174 miles per hour roughly. So that was the challenge. And so what from Bugatti's perspective is, how do I innovate in order to make the car lighter and faster and more aerodynamic? So one of the challenges then was for the vehicle that goes that fast, the wind tunnel only has a capacity of roughly 186 miles per hour. So how do you design something when you can't actually get the data within the wind tunnel? So what we had to do is we had to create a digital twin of the vehicle and then collect the data real time from the drivability of the current vehicle, and then take that data and then import that into the digital twin of a digital wind tunnel. So we use the simulation capabilities to actually then simulate what would happen at 280 some odd plus miles per hour. So when you look at the wing on the Bugatti, it serves a number of purposes. It allows the car to be more stable at different types of speeds and different driving dynamics. But at the same time, it also functions as an air brake. So when you're north of almost 300 miles per hour, you're going to have to stop quickly. And so the brakes are going to need a little bit of help. So that's what you see here is a simulation of that in the actual CAD. So in working together in partnership, what you see on the left-hand side is the original design that was pretty much hindered by conventional manufacturing modes, right? So you had your limitations, and this is what the design looked like on the left-hand side. So as we went through the whole design for additive manufacturing process, you see the reimagined part, or reimagined design on the right-hand side. So you can see it's considerably different. If you look at the bell crank, if you look at the shuttle, right, you see a lot of material that's been removed, light-weighted. And you also look at the tubes, which are now made out of carbon fiber, and then the attachment points have also been light-weighted. So considerable difference. So how did we get there? So if you look at our whole process of what we call the digital enterprise in creating a digital twin of a product, is we want to make sure that we do everything in a virtual environment that we possibly can, from designing the part to actually simulating the product, right, and validating that design, as well as then when we get into production, is validating the production component. So in this case, what we're doing is we're using one product to actually do the design and validation, and then as far as printing, to actually validate that print process in the virtual environment in the build envelope, so that when we get to the point of real production, we don't have a lot of surprises. So in a conventional mode, we've been doing this for a long time in managing the entire process and validating. Specifically, a lot of our customers, you know, before they put a shovel in the ground, they already know what that product is going to do, and as far as the manufacturing facility, how that manufacturing facility is going to look, and what type of production capabilities you're going to have. So we're doing the same thing now for additive. And then so that by the time you get to the product out in the field, that we're able to monitor that product and take that feedback from the field, from manufacturing, from the simulation, and continuously bring that back in for a closed loop system back into the design. So what you're doing is you're doing continuous improvement over and over again on your products. And that's particularly really important for additive manufacturing, because trying to get in a production environment, I would say about 80% to 90% is still between the engineer's ears, right? So all the wonderful tools and the artificial intelligence that we have for conventional manufacturing, for design, those things aren't there for additive yet, right? So we have what I call, I've coined a healthy impatience with our customers, because they're so used to having all these capabilities in conventional mode, because we know how materials react, we know how the automation works, we can pull off just about every piece of information you can possibly want off of a PLC. But when it comes to additive, that's where the work is, right? And so we're working very hard in order to have a system available in order to facilitate that. And that's what we did for Bugatti. If you want to see me afterwards or get in contact with me, you have a nice video from Mr. Gutsa talking a little bit more detail of what we did around this Bugatti wing. So let's look at what are the things that we achieved with this reimagined part. So we really accelerated the innovation process tenfold, and we reduced the aerodynamic drag for the vehicle. And really importantly, we lightweighted the system by 50%. So now let's shift gears. Let's talk about Siemens. You know, do we eat our own dog food? As I mentioned, you know, we make industrialized products, as well as we provide the software. And so we use that within Siemens for our own products. And so this is an example of that within power generation. So if you think about one of these the burners that we have for our power generation, we had to come up with a way to make it more efficient, require less maintenance, and actually use less fuel. So we had a situation in a sales environment where we were in a competitive state, and that was an issue. So we had to figure out how to innovate quickly, right? And instead of redesigning the entire power unit, we decided to focus in on one particular item, which is the actual burner. There we go. So the conventional approach on the left-hand side, you can see that it was made out of 13 parts, and it was joined with 18 welds. It required a thermal barrier coating on the front of it. And then we had to have an external pilot gas feed that was separate to that. And the lead time started at around 26 weeks, and that's without the thermal barrier coating. And then we had a weight of 4.5 kilograms. So I don't have the actual burner assembly with me, which is about yay big, but I have the mini-me version. So if anybody wants to see this later, you're more than welcome to come and talk to me about it. So when we went through the whole design for additive manufacturing process for this burner, we actually redesigned it to one single part. So the pilot gas feed is now internal component within the one part. We've optimized the cooling, and in some cases removed the need for the thermal barrier coating. The lead time has gone down to 3 weeks, and we also reduced the weight down to 3.5 kilograms. So as I mentioned before, it's very important for us within Siemens to industrialize additive manufacturing, just because, again, we produce products just like most of you folks out there, right? So we're very motivated to make sure that we're on the cutting edge with additive manufacturing. So how did we go through that exercise on the burner? Same thing, right? We invoked a digital twin. And so we made sure that we validated and designed everything in the virtual environment. And then so when we were ready to print, all we needed to do in this case was make some tweaks. Again, as I'm mentioning, right, a lot of the information is between the engineers' ears on making a repeatable part successful today. And then doing the continuous improvement loop. So as far as just incorporating how we've industrialized the additive manufacturing process, we're working with a lot of our partners into making sure that we're encompassing everything we possibly can within additive. And we're in a beta scenario right now with what we call our additive manufacturing network, in which we're allowing environment where engineers can actually come to a common place and get assistance on what machine should I use to print, what material should I use for a certain type of part, access to academia, access to think tanks like America Makes and access their storefront, as well as our partners from materials, on the materials side, the powder side, so that an engineer has everything at their fingertips in order to completely go through the design for additive manufacturing process. And once they've actually solidified the design, then utilize that same network to find a service bureau or service bureaus to put a bid out, right? And then to be able to select the service bureaus from there, and then eventually to be able to tie into the ERP or MES systems so that an engineer can track the order and make sure that they're going to get delivery of their parts on time. So with that, I'd like to pass it over to Doug Ramsey from Hackrod.
All right, thank you very much, Chris. That was extremely interesting. There's a couple things you said there that really got my juices flowing. There's a convergence of technologies that are coming together, not just around additive manufacturing, but around computation, around design. If you listen to the presentations we had this morning, we had Renishaw, we had Sodic, we had Carbon, we had Ford, and we're talking about this 10-year journey, maybe 20-year journey, but really intensely a 10-year journey on getting all this technology to converge, whether it's generative design, material characterization, and fundamentally, we've got a lot of engineering know-how that's locked in heads. That's where it sits right now. I have a proposition. I think we're about to democratize a lot of that expertise. I think we're about to unlock it. And it's because of a convergence that's coming in dissimilar industries. Dissimilar industries, not necessarily companies that grew up as manufacturers, companies that grew up as gaming companies. Some of our biggest partners make games. And I want to tell you a story. We're a pure play industry 4.0 company. We like to say that all the time. People say, what on earth does that mean? It's about a convergence of cyber and physical technologies that are coming into the manufacturing space to democratize a lot of industrial assets that have been tied up in vertical stacks for 200 years. I think we're getting back to an artisanal world. I think we're re-empowering artists to design freely. I think that's the promise. So Hackrod, we're actually born out of a Hollywood studio. My co-founder, 4 years ago, was coming off his last movie. Mouse McCoy, I'll show you some videos here. Mouse was 25 years in Hollywood, a stunt director, motorcycle racer, had just finished Act of Valor with the US Navy SEALs. And he went into a deep research program because he was looking at everything that he had driven for 25 years. And said, wait, I think people are about to reinvent the toys I like to play with. Well, what does Detroit 2028 look like? If you believe that machine learning is coming this quickly and additive manufacturing has collapsed as much as it has in the last 10 years, what's about to happen in the next 10 years? So, 10 years ago, a couple multi-billion-dollar companies were born out of dorm rooms with kids that had basic digital skills. Who's on Facebook? Oh, come on. Thank you. One of the largest companies in the world, born out of a dorm room with a couple guys with a good idea. If you look at this convergence of technologies, can 3 kids out of a dorm room create a car company? Do they have access to the best tools in 10 years? Are we going to go that way? So we started writing a movie. It was Detroit 2028. We had a nice log line for the movie. Say when driving is outlawed, only outlaws will drive. And it's a bleak future if you're here and you like cars. And Detroit turns into a level 5 autonomous zone and nobody can drive in here anymore. Is that Detroit? Well, it begs interesting questions. And as we started to work on that movie, we said, wait, this feels like George Lucas, 1974. He's running around Hollywood and says, I want to make Star Wars. And every studio throws him out. They throw him out and say, you can't make that movie. We don't have that type of graphic power. He said, okay, I'll make a company. I'll make a company that can make the movie. And that's what we are, Hackrod. We actually birthed an industrial company out of a Hollywood studio to work with companies like Siemens and the rest of our industrial partners and OEMs all around the world to explore the edge of all of this convergence. And so I want to take you through that journey.
Imagine that you could design and build the car of your dreams as easy as playing a video game. The Hackrod digital manufacturing platform, powered by Siemens, is connecting virtual reality with artificial intelligence and advanced manufacturing to make this dream a reality. To prove this out, we started by sketching La Bandita, the car that we wanted, but nobody made. Quickly moving from sketch to full-scale photoreal 3D model in virtual reality. allowing us to perfect the design and aerodynamics digitally, moving back into the physical world and connecting with the Internet of Things. We deployed sensors and scanners to capture 50 years of automotive knowledge. We harvested massive data sets and used them to teach the artificial intelligence generative design engine what a car experiences. With artificial intelligence and machine learning, we have the power of hundreds of engineers at our fingertips, allowing us to grow optimized engineering solutions for our design requirements. These designs are too complex and expensive for traditional manufacturing. They have to be 3D printed. The synergy between Siemens software and hardware is allowing us to lead the way in large-scale 3D printing.
Really going well, Jim. We're doing things that have never been done before.
The fact that we'll be able to optimize for manufacturing and buildability, it'll open the doors.
We'll be first.
It's a realization. It's not pixie dust and unicorns.
We are now printing a full-scale car in aluminum. La Bandita is not a concept car. It's a proof of concept of an entirely new way to design and manufacture. And if you can build a car this way, you can build anything.
So that's the journey that we're on. We went very quiet for about 4 years. We birthed 2 sister companies, the 2 largest printing systems in the world. Big Metal Additive and Center Street Technologies, one in Boulder, Colorado, the other one in Youngstown beside America Makes. We're printing cars, but we're thinking differently about that digital thread that runs through it. And that's why it's so important for us to work with partners like Siemens. And I'm going to walk you through a little bit more of what we're doing with the printing systems. But I have to stress that these digital revolutions have collapsed industries that thought that they were fairly immune to this type of change. If you were in a rock band, not me, in the 90s, you had spent 30 years mastering your art, getting into studios. By 2001, Apple releases GarageBand. Now, kids are releasing albums in their bedroom. They're making millions doing that. 16 months after Kodak files for bankruptcy, GoPro has a multi-billion-dollar IPO because they thought differently about how the consumer wanted to interact with that content. This pancaking happens, and it's largely driven by a digital thread. But, okay, so those are pure digital examples, right? But we're here to talk about additive manufacturing. And going from bits and getting back to atoms is a hell of a challenge. And so we tried to take it head on.
I'm an expert in advanced manufacturing and materials. I've spent my career inventing materials, manufacturing processes for some of the most high-speed products on this planet. And off of it, I was recruited by Lockheed Martin Aeronautics to work in the Skunk Works. I worked in a group that was specifically focused on advanced manufacturing concepts. We were called Project Lightspeed. And we were going to change the paradigms of manufacturing. And my project to enter that group was to study and to determine how we were going to 3D print the next jet fighter with carbon nanotubes. When I was at Skunk Works, I had access to a lot of very sophisticated aerospace tools. I wanted to share these things. I wanted to create the kind of manufacturing capability that someone with less experience than me could use and build whatever it is of their dreams. Hackrod is in the perfect position. We're a brand new company. We're a clean sheet. we can make all of the right decisions coming out of the gate. When your goal is design without compromise, you need to transfer your design to your manufacturing in the most efficient and complete manner. We're taking advantage of the synergy between the NX software and the Sinumeric controller hardware. And when the Siemens software talks to the Siemens hardware, everything is smoother. And so our machine, driven by the right software connected to the right hardware, gives a faster, more efficient overall operation. My vision of 3D printing is much bigger than most people. This machine is 12 foot wide, 25 foot long. You could drive a truck inside this 3D printer. It has 8 foot of Z-axis. This machine is probably the biggest 3D printer right now, but more importantly, it's the most capable, because this machine combines additive extrusion-based 3D printing with 5-axis CNC machining and high-fidelity in-situ automated metrology. That's a game changer. We're printing the body of the hack rod La Bandita out of a carbon composite material, and it prints it oversized. It's a little rough, but that surface is going to be scanned with automated integrated metrology. Those data are then used to locate the part inside the preform. And then a multi-axis CNC operation reveals the beautiful body part. It deposits, machines, and validates. It's able to generate a product and a digital twin all at the same time. This technology enables the creative person that may not have the budget of a large corporation to pursue their dream, to pursue their manufacturing or their creation dream.
So through that partnership with Siemens, there's something really important Slade said, and that is that we're creating a digital twin out of the build. We're actually recording, we have in situ monitoring for every serial number part that comes off the plate. I've got a serial number matching it up to a digital file. Now we're talking about being able to control for quality, being able to control for traceability, and having a full CAD to product back to CAD system integrated into one platform. And the other thing that Slade said, I really want to emphasize, is that we're trying to make these machines affordable, trying to make them available. These should not be only available to a PhD metallurgist, who knows how to handle powder and operate a vacuum chamber. No, that's not the future. We're dealing with non-reactive materials on open cells, base plates, and we're going big with that technology. I didn't have enough time to play the other video. Feel free to come up and grab my card. This is our large metal machine. We're 12 feet by 6 feet, 40 inches of Z. We can print whole automotive chassis on that machine. It's exactly what we're doing. But what's particularly interesting about this machine is we have a tool swap out. We can do machining and deposition at the same time. In fact, we require it. Because when you're talking about multiple welds, I want to have a nice smooth surface. We print on a smooth surface every time. We record that. We create a digital twin out of it. And I have forgiveness in my structure when I print this way. And I can print fast. And the vision, as I started the talk, is to democratize this. I want those 3 kids to make a car company. Right now, if you make a car company, go ask Elon Musk if he's having a good time. Yeah. That's where I want the machine. I want the machine available to the public. I want it available to those 3 kids coming out of a dorm room, who aren't necessarily mechanical engineers, but they got access to the right types of tools, the right types of facilities, and they can reach across this convergence of capabilities. Physics-based game engines. Forget the millennials, Generation Z, they're all digital natives. I'm a digital immigrant. I remember the pain of dialing 9, okay? The kids think magazines are broken iPads. There's an expectation for mass customization. The tools are in our hands. This is where we're going to be in 2028. And yes, that's the movie we're making, but it's also the company we made. Because we wanted to build that. Okay, that is a California car. That has no doors, no windshield, no roof, but boy, that's fun. And that's the star of the movie. And that's what we call La Bandita. We are building these right now, but it's an irrational product. I'm not gonna build a run of 10,000 of these cars. I'm gonna build them in small batches. And the goal is to get to parity. And just to wrap up, I'm talking about a digital revolution. Well, Amazon now is, I believe it's the largest company in the United States. There was a day where Sears was the largest retailer in the United States that they have filed for bankruptcy within the last 60 days. This is Sears in Santa Barbara, California. It is now vacant. I think vacancy is an opportunity, guys. Bring manufacturing home, re-democratize it. Why aren't we letting kids play? All the tools are there. Go build companies. Go realize that convergence. Get rich doing it. Have some fun. I'll wrap up there. Feel free to reach out to me. I'll be around. Mouse is around. And glad to walk you through the story in more detail. Thank you.
Please welcome Desktop Metal founder and CEO, Rick Fulop.
Okay, thank you very much for having me, everyone. I'm going to tell you a little bit about our company, Desktop Metal, which is a little bit over 3 years old, and great to see lots of familiar faces in the audience. So today I'm going to talk a little bit about the challenges, the promise, and the approach that we have to production of metal parts, which I think is a little bit different than what's being pursued in the industry by other folks. If we look at the promise, I think the way that we're going to see parts evolve over the next decade is going to be a little bit different than what they look like in today's vehicles. Really, with the same materials, you'll be able to make parts that are 30 to 50% lighter, reach a new level of complexity, and do mass customization for different markets. And this is really the promise of the fourth industrial revolution that we've heard a lot about. We also will be able to increase the percentage of recyclable content in vehicles. There's an effort by the UN and World Economic Forum on something called circular mobility, which allows you to essentially have more content on, or promoting more content that's fully recyclable inside automotive products. And I think, while it's not a big deal today, I think in a decade, that's going to be more important. With 3D printing, as you know, you can do mass customization. You can do things like generative design. I have some parts here that this skateboard truck was modeled in our live part software, and you can get a significant weight savings. This is a multi-physics generative design tool that we've made available to the market, and has a number of features that are unavailable in other products. Like the ability to do dynamic loads and also do more than just loads. The engine in the future will be able to do thermal and optimize for flow and other things like that. So it's an exciting project that we have inside our company. Other benefits of 3D printing, as you know, include supply chain reengineering, the ability to print locally what you need and not have to inventory parts, things like that. And do assembly consolidation. This is a presentation. I'm borrowing 3 or 4 slides from Audi, who did a very good job at a recent talk. But this is an example of a part that's in powder bed fusion, which is currently I would say, the existing technology that people would look at for metal printing, where they took a component that was a casting and they take 12 parts and convert it into a single part. In that vehicle, the R8, they have 200 kilograms worth of those types of parts, so it's a significant benefit to be able to 3D print them. And really, you can change existing processes and gain new benefits. For example, in press and sinter, you're able to get, or versus press and sinter, you're able to get new geometric complexity with 3D printing versus castings. You can lightweight with generative design and assembly consolidation. In stampings, you can now do the 3D printing of the tooling and have more evolution of your designs, which is, I think, a big deal. This is that example of castings going to AM, where that vehicle, which has 200 kilograms of those parts, can now go to a generative or topologically optimized setup where they save a lot of weight per part. But there's challenges to this technology, and it's not broadly adopted yet. It was designed primarily for aerospace initially. And when you think of the challenges, there's three major areas that are a problem. One is you can't use the standard types of materials that you would want to use in automotive. Things like 8620, 4140, they're things that are difficult to print with powder bed fusion. It's also very, very expensive. It's almost $1 million of capex per metric ton produced per year. That's ridiculously expensive as a production process. And it's not fast. So it's difficult to take it to production. You have to find really specialized applications. And finally, the raw materials for powder bed fusion, there's in the range of $60 a kilogram, so it's very expensive. So those are the major challenges for that technology. And if you think of if you step away from the cost and speed, you have other issues like supports and you know, lack of automation in today's processes, and that leads to very high cost. So this is a model from Audi from that same presentation. So I'm putting data that somebody else who's an expert is presenting us what they think the cost structure of powder bed fusion is today. And they put it at approximately 700 euros per kilogram of part. I don't know that there's many components in a vehicle that cost 700 bucks a kilo. So, and that's, they say that if you do X, Y, and Z, by 2025 it'll be 500. And if miracles happen, by 2035, maybe it's 100. So I'll tell you a little bit about my background. I worked on automotive from 2002 through 2010. I started a company that was a major supplier to many OEMs. And after that period of time, I became the original backer of a company called Protolabs. Protolabs, who you may use in your prototyping setup, it's today a $3.5 billion market cap company. At the time, it was a startup when we got involved. But in 2012, Protolabs said, we're going to go into metal additive. And they ended up acquiring a company called Fine Line, which had 12 concept laser machines. At the time, it was the largest customer for concept laser. And that was my first exposure to metal printing, which is the reason we ended up starting Desktop Metal. And seeing all the difficulties in producing parts with powder bed fusion kind of sparked the idea that we have to separate the shaping of the part from the thermodynamic processing of the part so that you can reach the cost structure that would make sense, and so that you can use materials that are inherently inexpensive from the beginning, and you don't have to have oxygen control of the raw material, which is what drives a lot of the costs in alternate technologies. So the approach that we have is quite different. It's more similar to the way that you do powder metallurgy today in volume in vehicles. We have a mission to really make 3D printing accessible, not just for mass production, but also for prototyping. We're a very well-funded company. Close to $500 million in investment has gone into our company. We have a team that's world-class in material science, backing from leading companies like Ford and BMW, Google, etc. We have two products in the market, and they're bookended. On the far left is our studio system, and that's shipping in volume. That is the world's first metal printer that prints parts in your office or in an environment where you don't need special facilities. And that's a big deal because prior generation of metal printers like powder bed fusion required you to have special facilities, and they were very expensive. So if you're going to spend $700,000 to have something that's got a decent sized build envelope, it's too expensive for prototyping. So we're giving people an accessible way to do prototyping in the same place where they might be using a Fortus plastic printer or a stereolithography machine to do prototyping. Now they can do that with metal. So that was the genesis of that product line. And shortly after that, we started working on our production system, which uses an evolution of binder jetting technology. And I'll get into that in a minute. But first, let me tell you for 5 minutes some of the features of our studio system. So like I said earlier, this is the first office-friendly metal printing system available in the market. It's very affordable compared to a powder bed fusion system of similar build envelope. You don't need to have respirators or 480-volt three-phase or special facilities. And you have a wide range of materials that you can print with this process, many of which are not available to powder bed fusion. Things like H13 or 4140 are materials that are in very high demand in the automotive space, but are unavailable and unattainable with powder bed fusion. So that's some of the areas where this technology is very, very attractive. Or things like copper, which is not on this list, but is a material that's compatible with our process. If you're doing electric vehicles, you want to 3D print components, electrical components, that's a very interesting technology. And then it's very easy to change materials. It takes under 1 minute to change materials with our studio system versus having to spend a whole day cleaning a powder bed fusion machine and then risking contamination and all of that. So you get parts that are similar to casting. They're near net shape and with properties that are comparable to MPIF 35. So it's I would say it's between a casting and machine rolled stock in terms of what you get on the other end. Now let me switch topic and talk to you about our production system. This is a platform that is going to evolve over time. Our initial system has a build envelope that's 330 millimeters cubed. It can print parts at about 8 liters per hour. The second evolution of that machine is 750 millimeter long bed, so much larger than a typical powder bed fusion machine, and that prints parts at 12 liters an hour. But this architecture can scale in the future to faster speed. You see some of the pictures here of the process. Is approximately 2 seconds per layer, which is very fast for an additive system. If you see here on the left, powder bed fusion system is a vector-based process. It's kind of like comparing a dot matrix with a laser printer in terms of the throughput and the speed. And you're doing this with raw materials that are 80% cheaper than the raw materials that you'd be using in a powder bed fusion system. So significant benefits. There's a lot of special technology that we've put into this machine that is not available in any other binder jet process, like the ability to have a constant wave, so you can have very long spreading with the same powder bed uniformity throughout the bed. We have a proprietary separable supports technology that we use in our studio system that is very unique to support parts. The entire machine is built with hot swappable modules so that you can be up and running if you ever have a component that has any issues. And it's upgradable over time. And again, when you compare it to powder bed fusion, you end up with parts that are dramatically less expensive than conventional systems. For example, an EOS 400, there are trade-offs to our technology, and I'm happy to talk about it, but if you compare an EOS 400, which is the fastest machine from EOS, they're about 100 cubic centimeters per hour. Our production 750 machine is 12 liters an hour. Similar build envelope, dramatically higher productivity. And they are not able to do things like D2 tool steels or 4140 or a lot of the materials that are actually used in industry. If you compare it, for example, to other binder jetting systems like the HP Metal Jet, our inherent speed is about 4 times faster with a build envelope that's much larger, giving you much better productivity per day. And then we have some advantages to the way that our process works in that we have the ability to inert our system, so we can work with reactive metals. We have solvent recovery. Our process uses piezo heads, so that gives us the ability to work with solvents, which means we can work with low alloy steels. We can work with reactive materials. In the world of thermal inkjet, which is what HP uses, you can only work with water. And if you work with water, it's going to be very difficult to do low alloy steels reliably. It's going to be very difficult to do reactive materials. And so those are some of the differentiating features. This is an example part that we show often, and it's an impeller that BMW took to production. It's for a water pump. They took that to production with powder bed fusion. The cost was about $80 for that part. We can mass produce this part with our process around $5.60. So dramatic cost reduction. This is what it means to have a process that can take you to production with 3D printing. We have lots of companies in automotive that are adopting our process and our technology. We have an open house in January 30th. If any of you guys want to come see it, Peter Denmark standing right back there, and we'd be happy to welcome you and see the technology printing. We're starting to ship these systems in less than 30 days. Our first customer is receiving theirs. It will have limited availability this year to maybe a little under a dozen customers, but next year our goal is to have broad availability of this technology. We have a very nice order book that we've built around it, and this will be the first of a generation of machines that we will make available to the market using this technology. So with that, I want to thank you. I'm happy to answer any questions. And I have some parts here that showcases what the technology can do. If you want to come see me afterwards, I'm happy to show you what they look like. These are both generatively designed with our live part software. And all right, thank you very much, everybody.
Please welcome back to the stage Additive Manufacturing Media Editor-in-Chief, Pete Zielinski, who will moderate a panel discussion featuring today's speakers.
Thank you. So as promised, we're going to bring the speakers back up and open it up for questions. Yeah, come on, don't be shy. So we will have mics, I believe, circulating through the crowd, right? And in addition to the mic, I'm also going to repeat the question because this is being live streamed, and I'm not sure that the audience question will be heard. So I want people over the internet to understand the question too. Let me begin. You know, the main competitor to the adoption of additive is the rootedness and the momentum that the established legacy manufacturing processes have. So how does additive find its opportunities if there's already a production process up and running that's going pretty well and that people in the organization pretty well understand? I guess I'd be happy to hear anyone speak to that. Sure.
Yeah, can I jump right in? So prior to joining the team at Hackrod, I spent 12 years at Alcoa. So I really like castings and forgings and sheet and all that good old-fashioned product. It has a home. It's not going away. It's really rethinking how you're going to optimize structures going forward, that right place for additive to play. You know, for the most part, you know, we're printing a car. You know, is that a good idea to print 100% of a car? No. No, we're doing it because we're pushing the technology to the edge. You know, when we work with OEMs, we bring in a full mix of materials. And we think about the joining structures. We think about the optimized design, and we apply additive where it makes sense. So is it a direct threat against the incumbents? Of course it is. Of course there's going to be place outs. But if you're thinking creatively about how you're going to apply additive, I think you have a lot of room as a material supplier or as a tier 2.
Paul, we heard you talk about Carbon's 5-year partnership with Ford, and you've had the experience of watching how Ford has looked for the opportunities for additive, and had the same experience with other companies adopting Carbon's technology. Maybe talk about that a little bit.
Sure, I would echo what was stated earlier. There has to be some unique and compelling value associated with an application that can be done via additive in order for it to make sense. There are very established processes which are wonderfully efficient and have a lot of good reasons for being in place. So I think it's unrealistic to expect that there would be any good reason to change unless there's some unique value that comes from a part that can be produced in an additive fashion. That unique value could be a lot of different things, as we talked about. It could be because it could be made more efficiently and economically in a low volume scenario. It could be that there's some unique performance advantage that comes from additive because the part can be designed in such a way, like the lightweight examples that Rick went through. Or it could be because of a lattice structure or some unique structure that you can't injection mold, that you're able to get superior performance, as in the case of a midsole. So there has to be something very compelling from an application perspective of a unique value in order for it to make sense. Otherwise, why change?
So actually, I'm watching Rick balance on his knee a part that has been made conventionally in the past and now is made additively. Maybe talk about that.
Yes, this is a part from Milwaukee. It's a big company in the power tool business, and they had 30 steps in producing this part that goes down to 1 step, and they can mass customize it, which is something they couldn't do before without changing their tooling. And so I think, and now they can work with alloys also that they couldn't work before. So there's a lot of benefits. But no, at the end of the day, it comes down to economics. I mean, I think we're going to see adoption of powder bed fusion continue in implants and aerospace. But if we want to put it in cars in scale, outside of a Bugatti or something that's a supercar, it's going to be, you need to have a cost structure that's going to be under $50 a kilogram, because that's kind of where you'll end up in other production processes. Actually, the system that was developed for small parts has a break-even point around 100,000 units versus a casting. So if you consider that, there's a lot of cars that are producing lower volume than that, and then you have all the tooling benefits, get to production faster, et cetera. But it's economics at the end of the day. I think we're in the early days of additive, and the technology has to evolve and get more sophisticated. I think you'll see more powder bed fusion used in tooling, but if you're going to put it in volume in a car, you need to use processes that are more cost effective.
Do we have audience questions? Lady here.
Joy.
Joy Forsmark, Ford Motor Company. One of the biggest challenges that I see in adopting of additive, well, I guess it would be 2. First, additive is obviously more than one technology. But the biggest challenge that I see with working with design engineers to try and come up with parts or systems or assemblies that might be appropriate, especially in the automotive space, there's just not material data. There's not a lot of good design rules around things. People aren't familiar with these. And I have to say, while there's been a lot of progress in the processing simulation software out there, they're still not, there in terms of how you work with this. So I'm just curious in kind of where you guys see the timeline for moving forward with this. I think it's great for some of the low volume stuff. I think you can do the trial and error, but as we try to move to more and more volume production, where do you see that space moving?
So the audience member from Ford, that was a pretty rich question, and she's talking about, real power and real opportunities for additive, but if it's going to go into serious production, there's a lack of established design rules, there's a lack of material property data to draw on. Would you like to speak to that?
I think the key issue that we're having at the moment with additive is the lack of body of knowledge. really around it. That's whether you're talking about graduates coming out of school, whether you're talking about material data, or whether you're talking about how it's going to behave long term in the years to come. You know, to give you an example that we were talking about just in the green room, fatigue data. That's the big one, right? So the biggest problem with fatigue data is that it's a big investment to generate it. We all know that. And it's an investment not just in money, but in time, because obviously you've got to generate the parts, and then you've got to test and compile the data. Now, the companies that are going to invest the most time and money in that are going to be the companies where, to them, that is a lot of intellectual property, and they're not prepared to share it. So I think together as an industry, we need to work together, and that's where the formation of working groups around additive are going to be particularly useful, because it means we can try and share some of the load. Bearing in mind that, you know, even if you take just the laser powder bed machines, the subtle vagaries and differences between those machines means that even they aren't necessarily comparable.
I think Joy's totally right. This is like, we're like in the CNC industry before you had simulation tools. And today you wouldn't CNC a part without running a simulation and make sure you're not going to have collisions and other problems. And so I think it's going to take us some time, and it's a journey, and we're going to sort of climb the mountain over the next decade. I saw this happen in batteries. I was in the battery business supplying lots of different OEMs, and when we got into that, we sort of developed the first high-power lithium-ion batteries. And we knew we could make them last a long time, but we didn't have calendar life data, so how are you going to put in a car for 15 years? And we had to just do the work over a period of 3 to 5 years. Eventually we got design wins, and eventually get in cars, and there's data, and then it's going to take time, but I don't see any reasons why we wouldn't get there over the next decade and have broad adoption of this technology. So if we look back 2030, back to 2020, I think this will be the decade where you have broad adoption of additive in automotive, initially in 2 or 3 parts, that then become 30 parts, that then become 300 parts.
Yeah, she specifically asked about timeline. Rick suggests 2030. We could look back and find ourselves at a place where some of the need that she has been addressed, and we're considering additive as an established means of how we produce. It seems like you have a thought on that.
Yeah, so this is a great question, right? Because this is the Wild West of additive manufacturing. And I'm going to be very blunt, okay? In 2030, if we have radical patent reform legislation that is adopted globally in multiple jurisdictions, we might have a fighting chance to solve this. But right now, who's incentivized to give away their characterization material coming off a print bed? Nobody.
Right.
Okay? Who's incentivized to go explore and put that into a singular database that we would share across one platform? Well, I can name a lot of startup companies that are tinkering with that idea. They run into a brick wall when they get past the data sheet. The US government spent $2 billion on the Material Genome Initiative and got skinny databases, because when they reached into all of those federal grants, they discovered that each federal grant had a IP control management plan associated with it, and they were unable to wed dissimilar projects together in same material classes. The federal government tied their own hands. So if you're looking at a new powder bed system and you say, I want to play with some unique compositions and some unique chemistries, good luck. You're starting from scratch, but you're probably going to get 1 or 2 material companies that are going to get in bed with you, and you're going to spend a couple years wrangling about who made that discovery. And this is a big problem. This is a really big problem. And we're not thinking very cleverly about what we should be how we should be using machine learning, artificial intelligence, working on anonymization of some of this data to be able to share single pools of test data. Now, and I'll tell, well, sorry, one last thing. There's a reverse flow of power if you look at the patent applications in industry today. Go to the aerospace industries, go look at United Technologies, Boeing, GE. They're patenting the materials. And they're doing it mostly with computational tools off these systems. If you own a patent on a material class, you now have the ability to do a dictated specification of the build to print back to the person who's going to provide the feedstock. So I don't care if you're Coors Tech or you're Conic or your Precision Cast Parts, you're in the business of discovering materials, and now your customer owns a patent. 30 years, we better have patent reform if we're going to get past this.
Any other audience questions? There's a hand in back there.
Thank you. Good morning. I'm Robert Bedard, also from Ford Motor Company. One thing I didn't see in any of the presentations was your thoughts on multi-material printing. Could you maybe share a little bit about your thoughts or maybe road mapping of where you think that's going to come in the next few years? Thank you.
Another audience member, also from Ford, asking about multi-material printing, if any of the speakers can address that. Sure, Rick?
I think for the sort of bulk thermal processing approach, it's difficult to have multi-material printing because you have mismatch of consolidation rates, multiple materials. And this doesn't exist today, but I could see somebody build a powder bed fusion system in someday where you have some type of xerographic approach to depositing a single layer with multiple materials and then fuse them. You do have shrinkage in that layer as the metal consolidates, but it would be in Z. I think it could be controlled, but it would be pretty cool to have like maybe somebody takes, the way that a color laser printer works, where you have 5 drums, and each drum would have a different material, and then you would basically like deposit. That would be your recoder system, and then you'd basically have your fusion. But then to really pursue that, you'd have to probably decorate the metal so that it would stick to the drum, because it's conductive now. So there's a lot of work to, but I could see how somebody could design a multi-material powder bed fusion system. If there was, probably aerospace would have better need for that than us here in this room. Somebody wants to build a rocket nozzle, it's copper in one part, Inconel in another part, Hastelloy in another part, aluminum in another part. One day we'll have that.
Yeah, and from a polymer perspective, I think also it would require a new architecture. Our current architecture is a single material at a time. It's possible to bake parts together during the thermal cure, so 2 different polymers that were produced independently can be cross-linked during the thermal cure. But it would require a different architecture. I think it's technically possible, but it's a ways off on the horizon.
So we're talking about production parts. There's a tooling application of additive too, and I wonder, Evan, do you confront these kind of questions and these kind of challenges as far as the reliability or the performance that can be expected from mold tooling that's made additively? Has it proven itself to be reliable and bulletproof at this point?
I would say that in general, it has proven to be reliable and bulletproof. The challenge with tooling is that it's very geometry driven. So you can have tools that have very kind of fragile geometries where you have really intricate details that protrude out from the part. And those areas are obviously going to be much more susceptible to any kind of breakage or wear, versus if you have something that's much simpler, a lot shallower sort of features that aren't going to face the same kind of forces. So I think that's something that's an area where it requires probably the most testing kind of moving forward. But in terms of characterizing the material properties and being certain that your tools will behave the same way as an equivalent design, I think that's where we're at right now.
Audience questions. Hand up here.
Hi, Andrew Holland from Mayflower Consulting, Lightweighting World. A question for Paul. On the parts for the Raptor and the GT500, I didn't see a traditional Tier 1, Tier 2. Does that mean you make the part, or does Ford make it in-house? And maybe if Ford is in-house, is that a future trend with additive?
So the audience member was a question to Carbon related to the Ford work, sort of observing, I didn't see a supplier involved. Does that mean the parts are made in-house, and is that the way it's going to go with additive?
So Ford has talked publicly about the fact that they're producing these parts themselves at their advanced manufacturing center excuse me, in Redford. So they're doing this production themselves. Whether that's a trend, I don't know. You would have to ask Ford or others. Carbon itself, we're not in the business of producing parts necessarily. We provide the technology to our customers to provide those parts, to produce those parts, and to suppliers to provide parts for OEMs or others. So we'll see how things change for the industry over time.
Clearly, the adoption of additive would be transformative to supply chains. And I wonder if anyone has a comment on that. We think about things like design freedom and material freedom, but there are logistics savings, assembly savings, organizational savings that flow from additive. Any thoughts on the way manufacturing organizations might change as a result of additive?
Absolutely. I think that you touched on a lot of the key points there, and it's because the processes are digital, they can be quite distributed. It's very likely and very possible to have production taking place around the world in locations close to consumption or close to assembly, and it can really change how parts are made and how they're distributed and assembled together. So I think there's a huge potential there. It's not inconceivable to think about these parts being produced on demand very close to consumers. And because they're digital files that can be distributed easily, the same part can be produced anywhere around the world. You're not constrained by a physical tool where you might have one or a couple of these physical tools.
I think before that kind of thing can actually come into effect, the control systems and monitoring systems that are being used need to be much more effective. I mean, we're at an auto show, so I'm going to quote a tire company, "Power is nothing without control." You know, having the ability to produce using different machines in different locations is one thing, but ensuring consistency of product is quite another. And what we're seeing, especially with the introduction of the latest machines, there's a big rush towards multiple lasers and larger build areas, you know, and in-process monitoring, but there's less talk about in-process control and actually ensuring that the products coming off of the machines are predictable in quality.
So I agree with everything that's been said. I think that's exactly right. The wrinkle that I would layer onto that is think about the legacy infrastructures that you have there in terms of who was building and who was buying, right? Okay, so if I'm making a fuel nozzle today, I'll make a lot of 50 for those. I'm probably going to cast them, going to ship them from a single plant. You're going to receive them, going to give you a warranty with that order. Now I'm going to send you a digital file that is endlessly repeatable at any given facility that you have around the world. Haven't I just destroyed my own business as a fuel nozzle provider? So what is the digital solve for that, okay? You know, now I need to have a crypto layer where I have some control over that file. And whether you're the buyer, the designer, or the producer, you know, I hate to say blockchain, but here we are, right? It's a lot better than Bitcoin. But we're going to talk about using these types of systems. So when I do design that part, and I have intellectual property that I did in Warren, Michigan, I send it to Kuala Lumpur. It's produced off a machine that's been certified. It has the right controls and measures. But now I have some reach back on that file where I'm going to give you a digital warranty on that, assuming that you print it to that specification, but I'm going to pull the file back, okay? I believe that that architecture must come. You know, otherwise, we're going to create entirely different corporate buying and making organizations. If we want to do that, that's another Wild West.
More from the audience? Hand right here.
Hi, Zach Kadikowski from Ford. So we've discussed, you know, how this is potentially a disruptive technology, and we've also dived into a lot of the major challenges that we're going to be addressing, you know, over the next 10 plus years. And I think it'll be easy for companies to get easily overwhelmed by all those challenges. But as companies are trying to today increase the rate of adoption, is there a single area of focus or maybe a single quick action that you might see that would help really allow companies or individuals to help speed up the rate of adoption of AM?
Yes.
So the question had to do with there are various obstacles in an established manufacturing organization that impede the adoption of additive, but is there a quick first step to take? Is there a good initial commitment to take that sort of gets you launched into additive effectively? Am I being fair? And yeah.
Without wanting to be facetious, yes, you need to get involved now. we need to, the only way to start developing the knowledge in-house is actually having the equipment in place and actually learning with it. At the moment, we are not in a phase where additive manufacturing is a volume manufacturing technology, right? Let's be serious. We have people using it in manufacturing, but mass production is not there yet. It won't get there until the users are experienced enough with it to drive it that way. If people aren't involved in additive in a serious way, and it's not just a case of buying a machine and closing doors and keeping that information to yourself, we've got to spread the knowledge around wider.
Rick?
I think Zach brings up a good point, and I think really for that adoption to happen, you kind of have to solve the question that Joy posed in at the beginning. It's like, we as manufacturers need to make the lives of our customers easy so that there's adoption of technology. Spec sheets should have an average of 300 tensile bar specimen analysis on every orientation. You got to have like machine-to-machine variability data. You got to have basically real process control. We got to put multispectral imaging on this thing so we could build a twin as we build the parts. We got to have all sorts of controls on every step of the process. And I think we're going to get there, and I think it's not going to take as long as many people think. It's going to take. It's a very vibrant and competitive space with significant amount of investment in R&D. And what we need to do to get there is not rocket science. So the basic process is, we all are building on different processes that essentially stand on the shoulders of giants. I mean, binder jetting was discovered and invented at MIT a little over 20 years ago, and it's just taken the evolution of inkjet and other things to make it competitive. Stereolithography, same thing, almost 30 years ago, and it's now this two-step curing process and other evolution that gives it the special properties, and it's just so on and so forth. That's what's enabling today's move from prototyping into production. So I think manufacturers that don't have this type of data in 24 months won't be competitive. You just have to make your customers' lives easier, or there won't be adoption. And I think we're working on it. We certainly want to make our customers successful. Their success is our success, so we're going to be as open as possible with them about the technology.
One thing that I'd want to add to that, we had spoken a little bit in the green room about, I think a lot of new users think too much about the wrong things and don't think enough about some of the other things. The things that really matter are often things that you already know or should know in terms of what your actual goals are, what's going to add value, make you more profitable. Those are things that you already know, and those are the things that you should be thinking probably more about. It's very easy to get lost in the weeds. In the course of a 30-minute panel, we can talk about 20 different technologies that we're working on, different things that we'd like to see, different things that would make our lives easier. But I think coming back to the fact of just getting involved and kind of learning, doing the design iterations, doing the prototypes, learning kind of how your kind of family of systems that you're interested in, how those work. And I think that that's probably the biggest determiner of success. I can say anecdotally, at least, our customers are most successful when they get their feet wet and they in a sense, just do it. We have one customer that has been using their equipment for about 1.5 years, and they've kept a backlog of about 3 months of work just doing development and prototypes and iterations of things. And they're at a point where they can easily see now a path forward from having done all of the legwork, all of the work that's specifically related to what they need to get out of their equipment. And from there, now they can see exactly where the profit's going to come from.
Yeah. And I would agree. And the only thing I would add is that while there's, in many ways, it's quite easy to get started. These are tools that are often available either in-house or with service providers or companies who have these tools and can produce parts. So that way it's easy to get a little bit started. But to really be serious about it and have a vision for production and to take things into production, because it affects a whole organization, it does require executive sponsorship and organizational commitment and kind of a common vision that this is something that that you want to have happen inside of your companies. Because a lot of people are going to need to get involved in order to take something into production. And again, for very good reason. But there's an organizational change aspect to this that I think shouldn't be understated, that it really requires sponsorship to implement.
That's great. That tees up exactly where I was hoping to go. So you're asking for the one thing that you can do. It's all in the hands of your designers. Okay? I have great confidence that in 3 to 4 years, every system that's made here is going to be improved by umpteen%, right? Okay? So we're all omnivores and we expect change to happen in the systems. We expect change to happen in the materials. The promise of additive is being able to be extremely creative with that new design parameters that you have, right? And if you're not using an augmented CAD system, a generative design system, and really thinking differently about what you can do with these systems, you're missing the forest for the trees, right? So I wouldn't mess around with the powders. I wouldn't worry about the characterization. I wouldn't get deeply into the machine right now. But I'd go cluster those designers together, which is the human capital, and say we're going to think differently about what we can do.
One more question, I think. Maybe two.
Hey there, this is Bruce from Haraeus. I had one question for Paul and one question for Evan. Paul, you had mentioned that Carbon does layerless parts, and I just wanted to see if you could expand on that a little bit. Sure. And Evan, you had mentioned that you could use, you could make broken molds could be reprinted from the break point, and I wanted to see if you could expand on that, just understanding, is that something that is in theory, or is it something that you're doing today?
Sure, so I'll start. Yes, as I mentioned earlier, our parts are not built in a layer by layer process. So that as a result, the end part has consistent mechanical properties in all directions. And the way that we're able to achieve that is we start with liquid resins. It's a resin-based system. So we start with liquid resins that we hold in a cassette, a bowl. At the bottom of that bowl is a window, and below that window is a light engine, a light projection system. And we project images of the part through that window. And the window is engineered in such a way that allows the light to shine through, and when the light shines through, it hardens the resin. But we also allow oxygen to flow through that window. And oxygen works in a manner that's polar opposite to the light. The light, when it strikes the resin, it hardens it. Oxygen prevents it from hardening just enough so that it doesn't stick to the top surface of the window. So we're able to then grow a part out of that liquid resin in a fashion that's not layer by layer. We're effectively curing on top of a continuous liquid interface that's on top of the window. So we grow that. It's a little bit easier to show visually than describe, and I'm happy to go into more detail with anybody who's interested. But the consequence of that process is that the parts themselves don't have any layers associated with them.
So his question was two-part, had to do with the digital light synthesis, and then also asked about the promise of repairing existing mold tooling.
So that is actually pretty straightforward. That's something that we're doing today, and that's probably one of the simpler applications in the sense that the design is already done, and for the most part, the program at that point would already be done. You'd already have your model of what you're trying to build. The only caveat would be that you'd have to, wherever the breakpoint is, from that site upwards in the Z direction, that would all need to be removed. So you'd have to basically plane that off and then regrow from the point of breakage or from the point of wear. But that's something that we're doing today. That's a relatively straightforward proposition.
So my clock says 0, but let's take one more question. Is there and he's right there.
Hi, my name's Mark Sendo from Big Air Technologies. So we're in the process of building a tile about 3 by 3 feet, hexagon shape, kind of complex design, and I was wondering if anyone had a solution using HDPE as the materials that would utilize 3D printing versus plaster injection molding.
A 3 by 3 tile made of HDPE, and looking for an additive solution for that.
Well, because it's polymers, I guess I'll respond. That's bigger than our current build envelope for the printers that we have. We believe and know that it's possible to make larger formats. It is also possible to produce parts in sections and then bring them together. We'd have to look at the exact material requirements that you have to see if any of our materials were appropriate or not, but we could certainly take a look at that with you.
Rick?
You may be able to do that with FDM. You have some limitations to sort of Z strength is going to be anisotropic, but I believe you can FDM HDPE, and there's companies that have printers in that size range, several.
All right, let's end it there. Thank you. That concludes our additive manufacturing workshop. Thank you so much for coming, giving your time. Thank you to our speakers.